Hi, I'm going to talk about binary numbers today. Binary, what does binary numbers mean? Well, bi means 2, so binary numbers are base 2 numbers. Well, what's a number base? Well, that really defines the place value of a number. So if we have a number, well, a number 1, or we have another number over here, we're talking regular numbers, what we call regular numbers, the numbers we work with every day. Those are decimal numbers, sometimes written with a little 10 in the lower right hand corner to signify that these are interpreted as decimal numbers. So we know this number is 11. That's this many objects, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Those dots are actually lines. In any case, 11 objects. Binary is only has this, well, a decimal number has 10 numbers possible in each column. The 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Those are individual decimal digits that can be used in any given place. So we can put a number 0 through 9 here. We can put 0 through 9 here. That's the palette of objects that we have to draw from. In a binary number, I could draw exactly the same thing, 1, 1, but interpret that as base 2. We have just 2 digits that we can draw from to populate those columns. That's the number 0 and 1. And we don't have these numbers. Binary, 2 numbers, decimal 10, so decimal has 10 digits, binary has 2 digits. By convention, we use 0 and 1 for that. Well, what earthly use are binary numbers? Well, computers like them. Computers like them because they're simple. You have values that are either on or off, either a voltage or no voltage, or a 0 or a 1. Turns out it's easier to design circuits that only have to deal with 2 states, 0 and 1, rather than 10 states, 0 through 9. Imagine you had to have, let's see, a graph here, and if this is voltage on this axis over here, and these are numbers on this axis over here. So this would be 0, 1, 2, 3, and so forth up to 9. And you had a bunch of different voltages levels here. Maybe 0 would be, let's change the color here. 0 would be, I think we'll change the color here. Right there, maybe the number 1 will be represented by this voltage. Number 2 will be represented by that voltage. Number 3 by that voltage, etc. So if you count it from 0 to 1, and then 1 to 2, and then 2 to 3, you can see how this would kind of stair step up. But you'd have to have a whole bunch of different voltages to indicate this. That would not be a digital system. That would be more closely approximate an analog system, an analog being continuous voltage changes. And we used to have analog computers. They operated in different principles. But the point here is that binary numbers are just very useful. Okay, so how do we work with binary numbers? Okay. So if we have a number 1, that's one way of, and this is looking at this base 2. What that really means is this is 1 times 2, and over on this side I'm call this decimal. On this side, 1 times 2 is equal to 2. If we have a number that's 1, 0, in binary, the simple thing to remember is every time you add a digit to the left, you double the previous column. So if this column here is the ones column, this column over here is double the ones, or 2 times 1, which is 2. So this would be the binary representation of the number 2. If we double this column again, like moving this column, doubling it, which puts a 1 in this column instead, that would be double times 2, which is 2 times 2, which is now 4. And again, if we move the 1 out this way and to the left again, this one would be double that one, because this moved over by 1. So that's, since the previous one was 4, that would be 2 times 4, double 4, is equal to 8. Okay? So, see a pattern here. 1, 2, 4, 8. Next one's going to be 16, 32, 64, 128, 256. Each digit moving over is double the previous one. Okay, look at this a little bit. Let's take a look at an example. So let's draw a box here and split it up into 4 equal parts. And we'll put in here digits. Let's see, there's a 1, there's a 1 there, there's nothing here, and there's a 1 there. Okay, so what we just learned up here, this is the ones column, this would be the twos column, next one would be 4. This is the weight of the digit that appears in that column, or the place value. Whoops. Too busy talking and not paying attention here. 1, 2, 4, 8, 16, 32, and so forth. We'll just stop and look at that one. Okay. So if we take, what is this number? Well, what we do here is we multiply each of these numbers by their place value. Well, in binary, the number is always going to be either 0 or 1. If it's 0, we just ignore it. Like this one here is an implied 0, so we just ignore this one. But every other one, we've got 1 times 8. This is 8, plus 1 times 2, which is 2, plus 1 times 1, which is 1, and that equals 8 plus 2 plus 1, which is, guess what? The number 11 in decimals. That's all we're doing here. I mean, this number stands by itself, and if you thought in binary like a computer, that's sufficient. Since us humans think in decimal, this purple stuff was just the conversion back to this decimal number. So to emphasize this number with blank is just a 0. So 1011 binary is equivalent to 11 decimal. Okay. Now let's take another example. And split those up just like before. So let's put a 1 in this column and a 1 in that column and leave the other ones blank. So if I leave it blank, that's an implied 0. So I'll just go ahead and put the zeros in there. Now remember the place values, that's 1, 2, 4, 8, And so now we can multiply these. 0 times 8 is 0, so ignore the ones with 0. 1 times 4 is 4. Ignore this one. 1 times 1 is 1, so 4 plus 1 is equal to 5. Decimal. This number, 101, is 5. And again, this is a binary number. Okay, well, this works okay. I got the 1, 2, 4, 8. But if I were to extend that out, and you look at the other columns over here, this would be, the next would be 16, it would be 32, and then 64, doubling each time, 128. You get out several places, get numbers like 32,768. Those numbers get real in a hurry if you've got more than just a few binary digits. So there's a shorthand way of looking at that. We'll draw another box here. Just like before. So rather than 1, 2, 4, and 8, and so forth, we can use a mathematical shorthand by using powers. So this is, since this is a binary, this place value is 1. You could also call that 2 to the 0. Now 2 to the 0 is the same thing as 1. Anything to the 0 is 1. 34,723 to the 0 power is equal to 1. Anything to the 0 power is equal to 1 except 0 itself. That is not equal to 1. But any non-zero base here to a power, power 0 is equal to 1. So that's just a definition, not intuitively obvious. So the next place value would be 2 to the first. This one would be 2 to the second. This one would be 2 to the third. Dot, dot, dot. We get out here, this one will be 2 to the 16th power, if I did that right. I might be off by a factor of 2. But that's the idea. This is a lot easier to draw this construct and a lot more obvious what digit it is. If this is the 0 digit, and this is the 1 digit, this is the second digit, and the third digit, this is the 16th digit out here. Much easier to understand than 32,768, for example. So, and just to expand on these powers a bit here, I've said that 2 to the 0 is equal to 1. 2 to the first power is, well, anything to the 1 to the power of 1 is equal to itself. So again, let's use that same big number over here, 32,723. To the 1 power is equal to 34,723. It's just equal to itself. So far this doesn't seem to be much value to you. Now let's get to 2 to the second power, which is the same as 2 squared. A number squared is a number multiplied by itself. And 2 times 2 is, yep, you guessed it, 4. Just remember that we're talking here in the decimal number system. 2 to the third power is equal to 3 of those 2's multiplied together. 2 times 2 times 2. Well, we just said 2 times 2 is equal to 4, so 4 times 2 is equal to 8. And you can see where this is going. This is just what we were talking about before. 1, 2, 4, 8. Here's the 1, 2, 4, 8. And that, very simply, is binary numbers explained, what they are and how they translate back to the decimal world.